obviously you want to have the strongest interaction. You want to have the most strongest entire state. So that is the thing. That's all.
Okay, thank you.
Okay. So as we are running out of time, we'll keep
sure.
for later. You can always catch up Professor Mitra later on.
Yeah, the papers. So basically, if I just do one thing, like you can take a screenshot of these 3 papers. Okay, so you can just take a screenshot of these 3 papers and read them later. Okay.
Yeah.
Right.
So let us thank Professor Mitra for an interesting topics. Okay.
Thank you. Okay.
Yeah. So now, in addition, he has also worked as a postdoctoral researcher at Macquarie University, Australia, and Institute of Quantum Computing. Currently, he serves as a senior lecturer at Macquarie University, Australia. Dr. Berry is an esteemed member of renowned professional organizations such as Australian Institute of Physics, American Physical Society, Optical Society of America, and Australian Optical Society. His research focuses on the field of quantum information and quantum optics. In the realm of quantum information, Dr. Berry has made significant contributions by developing highly efficient algorithms for simulating various physical systems. These algorithms have paved the way for groundbreaking quantum algorithms. In the field of quantum optics, he has pioneered in the development of exceptionally accurate methods for measuring optical phase through the use of adaptive techniques. Furthermore, Dr. Berry actively collaborates with various experimental groups to demonstrate the practical implementation of these methods. So today he will be talking on new methods in quantum simulation of chemistry. So I request Dr. Berry to take and present a very interesting topic. Dr. Berry.
Yep. Okay. Can everyone hear me and see the slides?
Yeah, we can hear you and slides as well.
Good. So today I will be giving a bit of a summary of the various methods for Hamiltonian simulation, and in particular for quantum chemistry. There's quite a lot of slides here. I'll be skipping over the technical parts, and I noticed that it asked me to keep the talk to 45 minutes with 15 minutes for questions. So if people want to know more about the particular parts of it, they can ask about that in the 15 minutes, and we can go to some of the other slides that I'm skipping over. Okay, so this work is, a lot of it is done in collaboration with people at Google, and there's a lot of the experts in quantum chemistry there. So the motivation for why you want to solve quantum chemistry is that it can be used for solving very important problems. So, for example, pharmaceutical design, or batteries for renewable energy, or designing catalysts for fixing nitrogen for fertilizer. So the general principle is that if you can simulate chemicals or materials, then you can predict their properties more rapidly than by synthesizing them directly. So this is a process which has been done extensively with classical computing, but the limitation is that as you're going to larger types of molecules that are more complicated, then the computation time goes up to be prohibitive for larger cases, and in particular what's called FOMOCO, which is involved in nitrogen fixing biologically, and that hasn't been possible to simulate with classical computing accurately. So this is a clear case where a quantum computing could give an advantage, but the challenge is to design the algorithms that are going to be the most efficient. So there's a whole lot of different types of Hamiltonian simulation algorithms. So the general idea is your system's represented by Hamiltonian. There's very general methods for simulating Hamiltonians, and then there's other methods which are more specifically designed for quantum chemistry. So I'll give you a bit of a summary of some of the most important methods for both of these. So a couple of the main results that I'll be talking about is on the left is for something that is suitable for molecules. So this would be suitable for, say, simulating for MoCo for catalysts, and the one on the right is more suitable for things like materials. And in the case of the molecules, you typically want to represent the system with a small number of orbitals, but you need to pre-compute a large amount of classical data that you're putting into the algorithm. And in the alternative case of periodic materials, you're using a simple basis where there's a small amount of data that goes in, but you have a large number of orbitals that you need to account for in your simulation. So we've developed some very efficient methods for both of these. So for the case of more general simulation of Hamiltonians, the general idea is you're trying to simulate evolution under the Hamiltonian. So this is an exponential of the Hamiltonian. You have an e to the minus IHT, gives you your time evolution under the Hamiltonian. And the original proposal by Seth Lloyd back in '96 was that you might have a Hamiltonian, which is a sum of a number of terms which are individually easy to simulate. So what you want to do is use a product formula. So you have a product of exponentials under the individual terms in the Hamiltonian to simulate your overall evolution. Now, if you just do an e to the minus IAT, e to the minus IBT, that's only going to be good for short t. So typically for longer times, you're breaking up your overall time into a number of subintervals and using this product formula on the subintervals. And you can use that very simple formula, which is what was proposed by Seth Lloyd, or you can use higher order product formulas. The most commonly discussed is the Suzuki product formulas, which are a systematic way of generating arbitrarily high order, where essentially it means that you have the error is going to be going like a delta t to some high power. But there's many other product formulas that you can use. Another approach which we proposed a bit more than 10 years ago now was using quantum walks. So the idea there is that instead of having just simulation on a single copy of your system, you have two copies of your system, and you construct a quantum walk operator, which is involving controlled reflections, which ends up giving you an operator which has eigenvalues related to the eigenvalues of your original Hamiltonian. So on the right, you can see a diagram of the complex plane where you have for an eigenvalue h of your Hamiltonian, two distinct eigenvalues of your walk operator. So the original proposal was to use this to generate evolution under the Hamiltonian with a range of different tricks. A further advance was to do a linear combination of unit trees. So the general idea of a linear combination of unit trees is that if you have some unit tree U, which is difficult to generate, but you have a number of unit trees UL, which are easy, and you can write your overall unit tree as a sum of these, then you can do this in a non-deterministic way where you have a control register, which is what's shown on as the top line here. You have a P, which is a state preparation, which gives you amplitudes going like the square roots of the weights. You do a controlled UL, and if you do an inverse preparation and measure 0 on that control register, then you've applied U to the target. But the problem here is that this is only happening with some small probability, which is governed by the sum of the weights. Now, the further advance on this was the insight that you could do amplitude amplification with just reflection on the control register, but not on the target register. So you have something that looks like this, for example, where you have this repeated linear combination of unitaries, and instead of a measurement, you have a reflection on that control register. And by doing that, you can deterministically implement the unitary on the target system. And in this example, this would be if you had an initial amplitude of 1/2 for success. If you have smaller amplitudes, you can do more of these steps of the oblivious amplitude amplification. And you can use this for a number of techniques, which I'll mention in a moment. But before that, you can also do what's called qubitization, where instead of doing this process of amplitude amplification, you can essentially just take this block where you would be trying to do a linear combination of unitaries and a reflection. But now what I've also done is I've replaced the UL, which we had before, with an HL. So instead of the U being a linear combination of unitaries, that you have your Hamiltonian being a linear combination of unitaries. And the trick now is that you get this same relation between the Hamiltonian and the eigenvalues as you did with this original quantum walk approach from 2012. And so you can use similar ideas for generating the evolution under the Hamiltonian. A further advance was by Low and Schwang, which was what's called quantum signal processing. So there, rather than trying to do a linear combination of unitaries, what you have is a top line which is indicating just a single qubit as a control. The W, which is being applied to the target system here, would be something like this walk operator. And the idea is that you can use a sequence of the single qubit rotations, which are indicated as S on the control, and these control W operations on the target system. And these individual S operations, they're not all going to be identical. They're going to be some very cleverly chosen sequence of rotations, such that at the end you have a high amplitude for just having 0 on the control, but you have a unitary performed on the target system. And that unitary is going to be the time-evolved system under the Hamiltonian. And the nice feature of this was that the complexity was approximately going as the norm of H times time plus a factor, a term which is logarithmic in the inverse error, whereas previous work was giving a multiplicative factor in this log 1 over epsilon. And in turn, in the first work, the complexity was roughly going like 1 over epsilon rather than a log of 1 over epsilon. So there's a whole progression of improvements in complexity in terms of how it's scaled with the allowable error. So one of the approaches for using a linear combination of unitaries is a Taylor series. So the idea there is that your Hamiltonian, you're writing as a linear combination of unitaries. Then you can do a Taylor series for the exponential, which is truncated at some value. Now, this time here needs to be relatively small so that you can accurately approximate it using a Taylor series. And then by expanding this exponential as a sum and then the H as a sum, you have a rather complicated sum for the exponential, but it's still a linear combination of unitaries, and you can apply it using the linear combination of unitaries approach. And that's what gives a complexity which is going like norm of H times time times a log of 1 over epsilon. Now, this is in itself not beating the complexity from quantum signal processing, but it can also be used as an inspiration for a similar approach for the time-dependent case. So if you have a Hamiltonian which is time-dependent, then essentially you're a power of h, which you have here. So instead of having h to the k, you would have a series of k integrals over time of the h. Now, this is something where you can discretize the integral over time and still give an overall complexity for the time-dependent simulation, which is going like norm of h times time times the log of 1 over epsilon. So that's useful in itself if you have a time-dependent Hamiltonian, but you can also use this idea for more efficient simulations, even if you have a time-independent Hamiltonian. So this was the insight of Low and Weeb, which was that you can use it for the interaction picture. So say if your Hamiltonian is a sum of a term A and a term B, then you can rotate B under the frame of A. So you have a new time-dependent B, which is like e to the IA, B e to the minus IAT. So that means you can approximate your time evolution by this rather complicated form in terms of multiple integrals of these products with the e to the evolution under A and the B. Now, the nice feature of this is it depends on the norm of B in terms of for its complexity. Now, if the norm of A is large, but the norm of B is small, then that means you're going to have a more efficient simulation. So there's a range of approaches that have been proposed for doing simulations that are more efficient using that. Another principle for more efficient simulation is the idea that rather than trying to generate the time evolution, we just want to estimate an energy. Now, if we're trying to estimate an energy, there's a standard method of doing controls. So you see there's a number of control registers at the top, which are being applied to a target register, which is your system. And the K ket there is indicating an eigenstate of the Hamiltonian with eigenvalue EK. So the idea is that if you're doing a eigenvalue measurement, you're going to be estimating this EK. Now, a further insight is that when we had these quantum walks and qubitization approaches, we were getting operators which were giving eigenvalues which were related to the eigenvalues of the Hamiltonian, but not exactly the same. So you can say, okay, instead of doing a controlled evolution under the Hamiltonian like this, we could do a controlled W squared, controlled W to fourth, and so forth. And we're going to estimate something which is like a plus or minus I arc sine EK over lambda. And if you're interested in what the EK is, you can just invert that arc sine. So that's just a sine. And that's going to give you, just by computation from that estimated value, the estimate of your EK. And a nice feature of this is it's essentially getting away from the entire complexity that you have from trying to generate the time evolution. So if you remember before, I was talking about there's the whole approach of quantum signal processing. Now, if you're only interested in estimating eigenvalues, then the quantum signal processing even though that's optimal for time evolution, it's not optimal if you're only interested in eigenvalues. If you're only interested in eigenvalues, you would just do a qubitization type of approach and do the phase estimation to estimate your energies. Now, I'll move on to talking about the case of quantum chemistry. Now, for quantum chemistry, you have, so if you remember, say, undergraduate, the treatment of the hydrogen atom, say, and you have various orbitals for the hydrogen atom, which are various eigenstates for the electron. Now, orbitals, when you're talking about molecules, are something similar, where instead of just looking at a single nucleus, you're now looking at multiple nuclei. And what you have is now essentially eigenstates of electrons, but you're also needing to address multiple electrons. So you might have these orbitals for electrons, but you don't just have a single electron in an orbital for your state. You have maybe one orbital that's occupied, another orbital that's occupied, another orbital that's occupied, and so forth. So typically what you're doing is you're describing your system by having a number of orbitals and saying, for each orbital, is it occupied by an electron or not occupied? Now, there's also the spin as well. You can have spin up and spin down for each orbital. So you should take that in, bear that in mind, but I'll just ignore that for simplicity in this description. Now, when you are describing molecules, typically what you're doing is designing some very clever set of orbitals which are describing a system fairly accurately, even though you only have a small number of orbitals. And in this case, you get a Hamiltonian that looks something like this. So what you have here are, you see, A daggers and A's. You might be familiar with these from quantum optics. But what these are here is actually fermionic annihilation and creation operators. So these will have anti-commutation relations rather than commutation relations, and they can only create a single fermion in an orbital, or a spin orbital. And if you see something where it has just a single annihilation and a single creation operator, what that's telling you is that this is describing a single electron hopping from orbital Q to orbital P. But you can also have 4 of these annihilation and creation operators, which are describing 2 electrons hopping at the same time. And physically, what this corresponds to is two electron interactions that you would get from the electron-electron potentials. Now, you'll see here you have these HPQs and HPQRSs. These are numbers, and these are computed by some rather complicated integrals. Now, these are integrals which can be computed efficiently, but with some difficulty on a classical computer. This is something that quantum chemists have been doing for many years, and very well-established software packages for this. But the difficulty is that it ends up being a large amount of classical data. And the difficulty we have with the quantum algorithms is that feeding large amounts of classical data into a quantum algorithm is difficult. And typically what you would be looking at is something like, say, a linear combination of unitaries or qubitization, where you have a P, which is a state preparation, which is giving you weights, which are corresponding to these HPQRSs. And now if you're looking at cases of interest where N is maybe 100 or larger, then you have 4 indices. If you have 4 indices and N is about 100, then this is looking like about 100 million for the number of items of data you're needing. So this is then going to be a very large complexity, which is scaling like the amount of data. Now, there's also a quantity which I'm calling lambda here. And this lambda will correspond to the sum of the weight. So it'd be like the sum of the absolute values of the HPQRSs. And this is what I was calling the norm of H earlier. So you have a feature where you have something where It's a product of essentially how large the Hamiltonian is and the amount of data in the description of the Hamiltonian. Now, if you're trying to, and achieving both of these at the same time is quite challenging. Now, another feature of these algorithms is that these are going to be implemented in a universal fault-tolerant quantum computer. Now, the leading proposals for this are where you have some large 2D array of qubits with logical qubits encoded in the surface code. Now, a fundamental feature of quantum codes is that you can't do all of the operations in a fault-tolerant way. So the typical case is where you can do what's called Clifford gates, which is simple things like NOT gates and control knots and Hadamards natively. But if you want to do a T gate, which is a phase, which is smaller than, it's like a fourth root of a Z gate, or the Toffoli, which is a controlled control knot. These are harder. So the Toffoli gate is a bit like a NAND gate if you're looking at a classical computing. And the Toffoli gate is a very, very, very important fundamental gate that appears all over the place in our quantum algorithms. So most of the time we're just counting Toffoli gates. Now, to do these, you have to do a distillation of what people call a magic state, which tends to be something which you can do fault tolerantly, but has a much larger cost than just doing a native Clifford gate. So for a lot of these algorithms, what we do is we actually count the Toffoli complexity. And the Toffoli complexity will actually end up giving you a complexity scaling like the square root of the amount of data needed to describe the Hamiltonian. So the total gate complexity might be going linearly in the amount of data, but the Toffoli complexity is going like the square root. And this is indicating that if we can work out some type of algorithm, and as well, I'll describe a little bit later where that square root is coming from, but if we can, this is giving us an improvement when we're just looking at the Toffoli complexity. Okay, so there's a few different descriptions to give a more compact description. So one of these is what's called a single factorization. Now, well, another one that I didn't mention here is just a sparse description. So you might just have a bunch of entries of HPQRS, which are close to zero, so you ignore them. That's fairly straightforward to describe. The single factorization is where you have an alternative description of this, where you have and I think I have, yeah, so essentially you have a factorization of the H. This is written slightly differently in the middle line, and so you have a factorization where you can describe it in terms of a number of weights, and for each of those weights you have something that essentially looks a bit like a one-body term, which is squared. Then you can do a double factorization, which is then taking that single factorization and doing a basis rotation on it, so it's behaving like just a number operator. And this was proposed by the Microsoft group back in 2021. I think the archive paper actually appeared in 2020, and that gave some very nice complexities and it reduced both the weighting, that lambda value that I mentioned, as well as the amount of data needed to describe the Hamiltonian. There it's a little bit more complicated now. The simple description of a complexity, which is going like a square root of the amount of data, doesn't quite hold because you have these unitaries U here, which you're wanting to implement as well. Now, our proposal was for using tensor hypercontraction. I've given the citation for an original proposal for tensor hypercontraction before, which wasn't actually for quantum algorithms, but we were applying this for quantum algorithms. So the idea now is that if you have a VPQRS, which is slightly modified from the HPQRS, you can describe it in terms of this zeta matrix and a chi matrix, and you have a sum over these mu and nu indices to give you an accurate approximation of your original two-body the terms there. So this in itself is a very promising, because it's turning something which would be of order n to the 4 in terms of the amount of data into something which is of order n squared, because you have these zetas and chi's which individually only have 2 indices. You have an m there which is a bit larger than n, the number of orbitals, but it's still not that much larger. So when you look at this type of description, you can rewrite it where you have a number of sums which are grouped together, and then you can identify that these sums are going to be corresponding to transformed annihilation and creation operators. Now, these individual C mu's, there's m of them rather than n, so these aren't actually mutually orthogonal things, but this is something which, even though it would normally be meaning you can't do it, because we would be applying this in a linear combination of unitaries, and we can do things independently in each branch of this linear combination of unitaries, it doesn't actually matter that these are non-orthogonal. And we can also then do individual basis rotations for these C's, and the overall lambda is decreased from this value at the top there on the, so it's in the middle right, to something which is just a sum over absolute values of those zetas. And that gives you a lambda value which is comparable or better than the double factorization, and the amount of data is improved over the double factorization as well. Keeping an eye on the time here, and maybe should skip over the asymptotics, but I'll just quickly mention that we have a description of how to do this by taking the annihilation and creation operators and describing them as strings of Pauli operators. And when you have the number operators, these just simplify to Z operators, just Pauli Zs. Now, technically, the number operator, it's like an identity minus Z over 2. And the identity can be separated out as a one-body term. So what I've shown here is the intrinsically two-body part of the Hamiltonian. There's a separate one-body term, which is easier to apply. So I'll give you a quick description of how you're inputting the data. So the data is input with something which is called a quantum ROM. So the idea is that you will have a control register where it is encoding some integer L, and you're going to try to output zero. You can do a bunch of C0 gates based on that particular data. If it's L equal to 1, you can do another controlled, multiply controlled Toffoli to control on that, and do C0s to output the data and so forth. Now, with the multiply controlled Toffelees, you can actually describe them in terms of individual Toffelees. And when you have a whole sequence of these, you can cancel a whole lot of the Toffelees so that the Toffele gate complexity ends up just being like the number of items of data. Now, what this means is that your Toffele complexity is going like the number of items of data. Now, this is a little bit different from the total amount of data because this is ignoring the actual complexity in terms of how many bits there are for each item of data. And since the data is being output with C-naughts are just Clifford gates, that doesn't contribute to the Toffele cost. Now, there's a further proposal by some people at Microsoft for improving this complexity where you're well, I won't go into the details here since we're short on time. This is very technical, but the overall idea is that if you look at the total amount of data rather than the items of data, so this would be basically number of items of data times the bits for each, you'll end up with a Toffele complexity that's going like the square root of that. And it's essentially a bit like a combination of the quantum ROM from here with ideas of QRAM, which is a bit older. There's now, when you're doing the state preparation, the quantum ROM can be used in combination with the idea which is like a coherent version of alias sampling to do your state preparation. And this basically means that the complexity of the state preparation is just going like the amount of data which is being used to describe the weights. So that's again something which is technical, so I'll skip over it and go down to some comparison of complexities. There was a number of simplifications that we did. We worked out ways of truncations for numbers of bits that are needed for various things. We recomputed the complexity from the von Berg double factorization approach and estimated a Toffele complexity of about 10 billion. So that's shown here. And whereas our complexity for tensor hypercontraction was about half that. Now, there's a caveat here that this is what's for a particular type of this is for simulating for MoCo, which is relevant for nitrogen fixing. Now, the caveat here is that this is for a particular set of orbitals by Ryer et al., but there's later work by Lee et al., which was giving a more accurate set of orbitals and arguing that the Ryer orbitals weren't actually sufficiently accurate. And you get about 6 times the complexity for that set of orbitals. So even though it's more accurate, it's significantly more difficult to simulate. And I'll skip over the asymptotics and go down to the plane wave basis, which is another major approach. So the idea of the plane wave basis is now to describe your system, which is likely to be some sort of periodic system like crystals, using plane waves rather than these very carefully chosen orbitals based on some configuration of nuclei. Now, the idea here is that you can calculate the coefficients, avoiding the need to input QROM into your algorithm. But the disadvantage now is that you're going to need a much larger number of orbitals because you need more plane waves to accurately simulate your system than you would with the Gaussian orbitals, which is what's used for molecules. And you also need to do some coherent arithmetic in the simulation as well, which also increases complexity. Now, the type of description which we're using is what's called first quantization, where you're recording the momentum for each electron. So this is like the when you're using plane waves, it's essentially like it's a wave number for each plane wave. And you are going to describe your quantum system by antisymmetric combinations of these basis states. And that's describing the antisymmetric property of electrons. Then you can describe your Hamiltonian as a sum of unitaries. So the key parts here are the first part on the left, which is kinetic energy, and the part at the bottom, which is describing the electron potential. And you'll see there that it has this 1/k² weighting there. So a major part of the difficulty is in applying that factor in the state preparation. Now, in the first quantization, which I'm showing on the right here now, this is what we were proposing. An earlier proposal by Lauren Weeb was to use second quantization, where you have a rather different description of the Hamiltonian. Now, for these types of approach, we want to use the interaction picture again. And this is the slide you've seen before. This is just to remind you what was happening. But if you are just comparing first and second quantization, you're going to be using either, so remember here with the interaction picture, you'd want to have, if B is something with a smaller norm, you would want to be applying it like this, where you'd have evolution under A as an e to the IAT, where B would be something which is applied as a linear combination of unitaries. Now, for first quantization, which is on the right here, you find that the V, that's the potential, tends to have a smaller norm. It has so the N here, the capital N, that's a number of orbitals, which is large. The eta is a number of electrons, which is far less. So you would take the V as like the B here. And in the other case, which is second quantization, you essentially have the eta, which is the number of electrons for first quantization, replaced with the capital N, the number of orbitals. And the reason for this is that the second quantization, you essentially end up with norms which are describing the worst state that can be represented. And in second quantization, this is essentially having a number of qubits representing all of the orbitals. And the worst state you can have is if all of the orbitals are occupied by electrons. Now, in reality, you wouldn't have all of those orbitals occupied by electrons, but for the description of the system, you're going to pay a cost corresponding to the worst state that can be represented, which would be the physically unrealistic case where all of the orbitals are occupied. But anyway, the result of this is that the kinetic energy then has the smaller norm, and you would want to apply the interaction picture in a different way. So the overall complexity that you end up with in the case of first quantization is a number of orbitals to the power of 1/3. So this is very, very good scaling of complexity as compared to prior work, which was typically at least linear in N. For the second quantization, you would get a complexity going like n² times an n to the 2/3, which is much worse with N, but you'll see there's not a factor of eta there. Now, if eta is significantly smaller, so remember eta is the number of electrons, if the number of electrons is significantly smaller than the number of orbitals, you're going to have a more efficient method with the first quantization and the interaction picture. And I see I've got about 3 minutes left if I'm taking 45 minutes for this. But another major question is, how efficient is the interaction picture going to be in reality? Because the interaction picture, it has to have this whole procedure with these discretized integrals, and you have to have a Dyson series up to some order, and you're going to get a logarithmic factor for the Dyson series and factors in the complexity from discretizing these integrals. And this all introduces a number of difficulties with the overall quantum algorithm. And we have done a whole lot of analysis for the complexity here and a whole lot of improvements in the overall the implementation. And we find that we have the types of complexities that look like this. So on the left is Toffoli count for qubitization. So look at the upper left, and on the upper right, it's in costs for the interaction picture. The lower part is costs and numbers of qubits as well. So, but you'll see there that for a wide range of parameters, qubitization is actually giving a lower Toffoli count than the interaction picture. So this is perhaps surprising based on the asymptotics, because for the asymptotics, it's indicating that the interaction picture should be best. But it then turns out that you would really need very, very large number of orbitals for this approach to be more efficient. And I've actually circled, or it's an ellipse around the points which are more efficient for the interaction picture. And you can see there that this delta, this is essentially a resolution of the grid. And the resolution of the grid of 10 to the minus 3 is much finer resolution than you would typically want to simulate. So this is indicating that typically your interaction picture wouldn't be the one you want to use, and you'd want to use a qubitization approach. There's a whole lot of interesting things there that I've skipped over, but in the interest of time, since I was asked to take 45 minutes for that, I'll just skip to the conclusions. So the conclusions here are that in the one case, we have Gaussian basis methods with tensor hypercontraction, which is giving the highest efficiency. And on the other hand, you have, for periodic materials, a very efficient simulation using plane waves. And even though the asymptotically most efficient one would be the interaction picture, it turns out that the qubitization is actually giving the best gate counts. So I'll hand it back to the host there and let you ask questions.
Okay, thank you, Dr. Bedi, for your nice presentations. So I would like to request the participants, if you have any questions, please feel free to ask.
Thank you for your talk.
Yes, please.
Yeah, for time-dependent Hamiltonian, I usually use Dyson series. So my question is, what should be the level of discretization of time parameter for efficient calculations required for finding eigenvalues and eigenvectors of time-dependent Hamiltonian?
It's a good question. I don't remember the formula off the top of my head. I have a couple of slides here that was talking about improving this complexity. So there was an original description of it, which was essentially using an approximation from the value at one bound on one side, and then an improved method which was giving a improved complexity depending on the second derivative. So this was roughly halving the number of bits that we needed in these in this. If I remember correctly, it was something like 10 bits that we were needing for these examples, whereas for a less efficient approach, it was about 20 bits for the time.
Okay.
So, but if you have something which has some poor behavior of the second derivative, then it might be not as efficient. But here, this is for the case where you're using it for the interaction picture.
Because issue comes when this entangling of non-commutable terms in the Hamiltonian comes. So this is something which is very important. So my second question, could you please suggest verification techniques used by you for time-dependent Hamiltonian? Because you will get some output results. How do you verify them?
That's a good question. So we're not typically looking at verification, except in the sense that we theoretically verify that our quantum algorithm is doing what it should. And if you have a quantum computer which is fault tolerant, then it should be actually implementing the algorithm as given. But that still requires you to be able to build a fault tolerant quantum computer. At the end of the day, if you're wanting to simulate some physical system, what you would be doing to verify it would be to work out predictions and synthesize the material and see if the predictions are actually matching with the measured properties of the material.
Thank you. Quickly, one more question. In your presentation, in one of your slides, you were mentioning about hypercontraction algorithm. So my question is this algorithm is part of TensorFlow package, or it is something
part
different?
Of what package, sorry?
TensorFlow.
I'm not familiar with that.
Okay. So this is algorithm which usually tensor networks related.
Well, tensor networks is a very different thing than the tensor hypercontraction, other than it's a tensor. So tensor networks is typically for classical computing to simulate quantum systems. The tensor hypercontraction is a description of the quantum Hamiltonian. But it's intended for implementation in a quantum computer.
Okay, so could you please name software packages which you use for Dyson series or relevant to this?
Well, we don't have a package which we used. I had hand wrote code to do counting of numbers of gates. So I think some of this was released with the paper. I'm not sure. I'd have to double check. I seem to remember that at least one of our papers, we released some code as well.
Thank you.
Yeah.
Okay, so thank you, Dr. Bedi, for such a nice presentation. So I guess we conclude our second talk here. Thank you very much, Professor Bedi.
Yep. Okay.